series on birational geometry characteristic T. And let me remind you, starting from next week, since the semester already started, so because of some schedule confliction, the lectures will be rescheduled, start at 3:35. So for the remaining lectures. And today, Professor Birkar will focus on adversarial business. Let's work on it.
So in today's lecture, I will mostly talk about surfaces. Surfaces, because the dimension is very low, we can do a lot of calculations, we can do a lot of things that we may not be able to do in higher dimensions. So this is much easier to understand compared to 3, 4, and so on. And I start from surfaces, not from curves from dimension 1, because in dimension 1, essentially, there is really no birational geometry. Very trivial, so not very interesting. This is the first non-trivial case. So first I will give you a little more general technical background. So there will be mostly definitions. So the first is about pairs. So as I said in the last lecture, if you have any questions, you just ask. You don't need to be shy. We have enough time, so you can really ask. So the first thing is pairs. A pair consists of a normal projective variety or non-necessarily projective. Let me also just fix an algebraic field characteristic P. So this is usually positive, but some of the definitions and many of the things that is can be also hold for characteristic 0. So a pair XB consists of a normal variety. So everything will be over K, X, and a so-called Q divisor. Divisor B. So the Q divisor just means that you have a linear combination of prime divisors. These are just irreducible subvarieties of dimension 1, just like hypersurfaces. And then you have some coefficients here, where the PI, in this case I assume rational, but they are also between 0 and 1. So in algebraic geometry or differential geometry, you have a divisor written in this form. Usually these coefficients are integers. But in birational geometry, we allow rational and sometimes even real coefficients. And this is very important for technical reasons. And this is maybe very important to remember. We like this coefficient to be 0, between 0 and 1, not larger. So this is a pair. If you are interested only in studying varieties alone, not with a divisor, this divisor somehow comes into the picture very naturally. So it's very, very useful to allow this divisor, not X alone. So I will tell you actually very soon why this is important. Maybe I also better introduce one class of singularities. We can also define singularities in the following form. We say XB is a log canonical. So for this talk, it is actually not really important, but maybe later talks will be important. We say that this is a log canonical if for every birational map from, let's say, Y to X, this is proper. Just projective. And you can also assume that the Y is normal So for example, the most important case will be when you take a resolution, if you know there is a resolution. So if you take any birational map of this form, and if you write, so you can, for some more or less trivial reasons, you can write a formula of this form. As you already have a canonical divisor or bundle over. So there is one thing I forgot here. I should say that such that it divides the kx plus b is q. So most of these things are technical. You don't need to worry so much about it. It will be clear later on why we put these conditions. Say q. And this means that some multiple of this is a Cartesian divisor. So because you have rational coefficients, then you need to multiply it by something to make them integers. But also because you have singularities, it's not smooth. It's not trivial that you can get a Caucher divisor. Sometimes you could have a failed divisor, even you multiply with any number, it never becomes Caucher. It's never locally defined by one polynomial. Anyway, as I said, you don't need to worry so much about these things for the moment. So if you take any one of these forms, especially a resolution, then you write a formula of this kind, and then we want coefficient of this divisor divide to be not more than 1. So maybe I give you one example. The most simple example would be just take, let's say, A2 and then take just some nice lines which are in a general position that they don't go through a point. So this is okay for us, but this is not okay. Or if you have a curve intersecting itself many times, these are not good. These are not canonical. So canonical, roughly speaking, means that singularities should not be too complicated. They should be relatively easy. Okay. So I'll tell you now why pairs are important than just varieties. And this formula should make it quite clear. So called a junction formula. Now suppose that we have x, b is a pair, and suppose that S is a prime divisor. This is the component of B with coefficient 1. So you might have many different components with different coefficients, but I assume that this one has coefficient 1. And these are usually the most important for the geometry of this pair. So we have a classical adjunction for here. Here the classical adjunction is that suppose that X is smooth and S also smooth, then you can say that canonical bundle of S is calculated by taking canonical bundle of X at the divisor S and then restrict it to this divisor. So you also have not only algebraic geometry but also differential geometry. So it's very classical. So in other words, the canonical bundle of S can be understood in terms of canonical bundle of X and the divisor itself. S. So this is classical, and this proof is not. And then we have the more general set. Okay, so let me also make it pretty simpler. Let's just put dimension of x to be 2. So we are on surfaces. But this actually also works in high dimension. So in the more general setting, what I do first is we can take a resolution, let's say y to x, such that we have a diagram of this form. We have the following. So we have first, we have a diagram, we have y to x, f, the s is a curve inside x, and then I can not only resolve the singularities of x, I can at the same time resolve the singularities of s also. So this just like blowing up things. And resolving singularities of s just gives you its normalization. So this guy is just normalization of. For curves, resolving singularities is the same as taking normalization. So I have a diagram of this form, but moreover, this sits also inside 1. So this is just about resolving singularities. There is nothing so special about it, and such that if I write again ky plus dy to be the full bracket, k plus p, then I can make sure that this dy is effective. It does not get any negative coefficient. But this is more like a surface geometry. In higher dimension, you should state it in a different way. Okay, so what I'm trying to do is to go on this resolution and then use this classical adjunction formula. So now I can say that if I restrict this divisor to this normalization, what I get is, I can write it in this form. Ky plus this is s normalized plus b minus s normalized and then restricted. So what I have done here, I just take the s out and leave it as it is. So if I restrict the first bit to this normalization, I just get ks normalized plus, I still have this bit left here. So now this is an effective divisor which does not contain the s itself. So when you restrict it to s, you get something again effective. So I can write it just as a definition. I can say this is ks non plus bs. And here, as I say, this divisor is effective. So why this is important? Just because you start from a pair and you get something which again looks like a pair. So in other words, if you try to do induction, so that in this case we are working on surfaces, you can understand this surface by using curves. And you can do that exactly because of this kind of formula, because you can relate the canonical bundle with the divisor p on x with something of smaller dimension. Of course, in general, the coefficients here could be more than 1, but if you have some good singularities, you can also make sure this is exactly as in the definition of space. So just as a remark, if this, for example, if it has low canonical singularities, then in fact what you get here is again low canonical. It is a pair with low canonical singularities. Well, in this setting here, this is just a curve with a variety of dimension 1. Low canonical exactly means that the coefficients are all not more than 1. They are between 0 and 1. So this is the junction formula. You will see in a minute why I need this kind of formula. So actually maybe I could just write it there. So this whole story is saying now, note that Kn plus Ts this is equal to the pullback of Kn plus P. This curve is not inside X. You don't have to pull back the divisor, but you get something which looks like a pair. Okay, so this is about pairs and the junction, and then I will define codiral dimension. So I have to make this a few definitions before we get to the more exciting part. Here, suppose that X is normal projective, and suppose that D is some cartio well. Then I define the codiral dimension of this divisor. So this is the smallest, or the largest number we will denote it by kappa of t, such that you calculate the limb sup of you take the number of sections of m times p, you divide it by m to the power. And I want this to be pi. So the formula maybe looks a little bit strange, but it actually has a very, very simple meaning. It just tells you that when you look at all these multiples of t and you look at the sections, the dimension of the space of sections, and that tells you how many sections you have. So the larger the codiral dimension means that the faster this becomes big. This grows faster and faster. So very roughly speaking, so this h0 of mt it looks like a polynomial. It's actually not a polynomial. So this looks like a polynomial of exactly the degree codiral dimension. So that's what it is. It just tells you that this number, this sequence of numbers, if you consider it as a function, it just behaves like a polynomial of degree exactly equal to the codiral dimension. And for some quite simple reasons, you can actually say a lot of things about this codiral dimension, so let's put it down in remarks. First, this number belongs to a very small set. This could be minus infinity, could be 0, 1, and could be up to the dimension of x. It cannot be more than that. And also I can know that if D is a rational divisor, in other words, it has rational coefficients, then we can also define the quadric dimension of D should be quadric dimension of maybe some large multiple of T. In other words, you can kill all the denominators and what you will have is all integers, not rational numbers. But it doesn't matter what n you take, because the way I have defined it is kind of asymptotic, so it doesn't really matter what n you take. So you can again define quadric dimension, and then there are some terminologies. If quadric dimension of D is equal to the dimension precisely, then we say there is a special name for this thing. We say that D is big, which makes sense to say it's big because this exactly means that you have so many sections that the divisor really is like a big divisor, like a big guy. So we have this terminology, and yeah, that's pretty much. If maybe I also just say one more thing. If x is, let's say, smooth, and T is equal to the canonical bundle, then the quadric dimension of this bundle is also called the quadric dimension of x itself. So after a very long time that people worked on algebraic geometry of surfaces, people realized that these numbers somehow put varieties, or in this case surfaces, into different categories that somehow they are very different from each other. So okay, maybe one more remark just in dimension 1. This has a very, again, simple meaning. And you can understand things more topologically. The quadric dimension of x negative exactly means that the genus is 0, which is just saying that x is P1. And quadric dimension be 0 exactly means that x is elliptic. Yeah. And quadric dimension. So here also you have genus 1. This being positive just means that genus is more than 1. So you have a topological also interpretation of this number quadric dimension. So already for curve, you see that different quadric dimensions will give you very different geometric things. So, for example, P1 is very different from geometric curve. Okay, let's leave this quadric dimension for the moment, and let me tell you something about minimal models. And more refined expression. Suppose that we have xp a projective pair. Now we say that suppose that we also have birational X to some other model Y. So again, Y here is a normal variety. And I could also define a divisor on Y. I just push down my divisor on B. So in many cases, this phi is actually amorphic, just like holomorphic. So you can actually just push down your divisor. Then I get essentially, I assume that I have a pair here. So all I have right now is essentially I start with a pair and I assume that I have another pair which is birational to the original. Now I say that we say that this y is we say that this is the minimal model. If I have some positivity property. So this is just something to remember, but more technically, what I mean is that this is net. So by definition, it means that intersection numbers are always non-negative. But intuitively, it just means that you have some kind of positivity property. And on the opposite side, we have a more refined space. Usually denoted by M and S. If instead of positivity, you have some kind of negativity. So this is a little more slightly different. What I require is that if there is some fine ratio, let's say from Y to Z, such that ky plus dy is essentially the opposite, is negative on the fiber. In other words, it intersects negatively curved inside the fiber. But I think it's quite good to remember that these two ways to work. You have here positivity, here you have negativity. Okay, so let me just explain a little bit why I define this kind of thing. So if you start with a pair, or if you start with just one single variety, then algebraic geometry is about understanding the geometry of this variety or pair. But in practice, it's very hard to understand the geometry if you just stay on the same variety. And people came up with the idea that instead of studying X itself, if you just instead of staying on X, why not you do some modifications and you go to another variety, but such that it's close enough to the original variety. And in practice, it just means birational. So in other words, if you lower your standard a little bit and say that, okay, you want to understand the variety only up to this kind of modifications, up to birational equivalent, then you will have a lot more flexibility. You have more tools, you can say a lot more than if you just stay on the same variety. And the idea of defining this thing is that when you start from XB, you try to find some other variety birational to X with this pair structure such that it has this kind of numerical properties. So the goal is to look for this kind of models. So the goal of the so-called minimal model program are actually just birational geometry, maybe I better say birational geometry. So we are interested in looking for such a very special kind of model. And what is the advantage of having this kind of model? Well, the advantage is that this kind of numerical conditions put very strong conditions on the geometry. It's much easier to say something about this model rather than the original one, because you have these conditions, and in fact these are not just numerical, but we also try to translate this thing into a little bit more geometry statements. For the second one is actually already geometric. You have this vibration, and when you are given a vibration, you can look at the fiber, you can look at the base, and you can try to understand the variety y in terms of the fiber and in terms of the set. So for example, if you are looking at the dimension 2 case, so this is a surface, and then you have a vibration over some other variety. So vibration here, it means that dimension actually drops. So for instance, you could have a surface fibered over a curve, and the fibers here are actually very special. They will be just like P1. So it's like you have a P1 bundle over a curve, and a P1 bundle is much easier to understand than just a random surface. Okay, so this is the goal of birational geometry, but the process of looking for such models is called the minimum model process. And usually we write it as MMPs, just minimum model program. So in other words, there is some kind of a program, algorithm, which tells you that when you start from XB, how to find this Y, dy. In the case of surfaces, I will actually tell you how to do it. So in dimension 1, as I said, it's not so interesting because Y dy is just equal to XB, so there is nothing so interesting to say. But for surfaces, it is much more complicated. Okay, so as before in this lecture, I will stay on characteristics. So here, characteristics. But the case of complex numbers actually works in a kind of similar. So the main theorem will be something of this form. This is the theorem for surfaces, or MLT for surfaces. Suppose that we have XP projected of dimension 2. And for simplicity, I also assume that X is smooth, but this actually doesn't really play such a big role. But on the other hand, it is not such a big deal, because if you start with whatever singular pair, you can take resolution and replace by this. So it's also not such a big assumption. So suppose that we have this kind of pair, and then the theorem says that there is a minimum model program, and this will be clear during the proof. which the program ends up with a minimum model or more refined space. Which I will denote by V1. And I also tell you the sketch of the proof. Okay, so we are given x, p, and we try to find the minimum model for more refined space. So I can first ask the question whether k plus b is already finite. So remember that means this positivity conditional intersection number. If it is net, then that means that we already have the minimum model. So there is nothing to do. But usually this is not the case. So assume that we don't have this positivity. Which simply means that there is some curve, let's say C with negative intersection number. Okay, so the x is not a minimum model, and then the idea is that you maybe can change your x somehow and end up with something positive or something vibration with some negativity. So how do we do? Well, first we can kind of cheat a little. Just pick an ample divisor. Let's say A. Now, k plus b is not positive, but if I add a lot of multiples of this ample divisor, it becomes positive for trivial reasons. So let t be the smallest number such that kx plus b plus ta times a is, well, net. So if I take t to be very large because of this ampleness, this also becomes ample. But I want to somehow take just the smallest, not any extra.
So in your definition of net, do you want the greater than 0 or greater equal? Somehow.
It always can be equal. It can be equal to 0 also. So if it is not enough, then you must have negativity. So maybe it's not very clear. It should be more than or equal. So net is not a strict kind of positivity, also it's like semi-positivity. Okay, so I take this t, I add the smallest possible multiple of a to get the net divisor. Now you could say that, okay, this is already like a minimum model. Why we should go any further? But the problem is that geometry of this divisor does not reflect the geometry of k plus b. We want to understand this, not that. So that's why I said this is really a cheat. But on the other hand, it's not such a bad idea for the following reason. So let me take a notation. Suppose this is equal to L. First, one thing to note here is that it turns out actually this number is not clear at all in general, that this number is actually rational. And this will be discussed in lecture 5. So let's leave that for the moment. But you don't really need to worry so much about it. Just assume that it's a rational number. Now, suppose that the L is So this L is nth, it has a numerical positivity, but assume that it has a geometric positivity. In other words, assume that L is what we call semi-ample. Semi-ample means that, so I introduce all this terminology so that you can just become more familiar with the language of birational geometry. So this just means that some multiple is free, generated by global section. So you might have to multiply this with a very large number, but it doesn't matter. It just means that some high multiple of it. This guy will be free, generated by global sections. It's actually also the same as saying that this is the pullback of some ample device. But here you might need rational coefficients. So these are all equivalent definitions. So yeah, assume this for the moment. Assume that this guy is semi-ample. So just from this definition here, it's the pullback of some ample divisors. It means that so there is some morphism. Let's say f from x to some other variety such that L is equal to the pullback of some ample, maybe q divided, something with rational coefficient. But the important thing is that it just gives you a morphism, gives you a non-trivial, in most cases, a non-trivial morphism, which is usually very difficult to construct. So we have this morphism, and then we have several cases. For instance, assume, now if L, so this divide the L is big, it's actually, you can characterize it in several different ways. It's big, remember means that largest polar dimension, but in this case, you can actually also characterize it as just saying that its self-intersection number is positive. It looks like an ample divisor. But it's also the same as saying that f is equal by a rational morphism. So this is one of the possibilities, that you just get a birational morphism. And because we are on the surface, a birational morphism just collapses finitely many curves, points, and leaves the roots of the variable intact. So if this is the case, I will put the time to be equal to the push down of B, and I will just continue exactly the same kind of, apply the same kind of arguments to my new pair. So I have X, I have collapsed. In fact, because K plus B is negative on some curve, this tells you definitely F is not an identity morphism. There will be some curves which are collapsed. And I get a new surface with a new boundary, and I just go back to the first step and I apply the same kind of process. So the point is that when you, on X prime, B prime, you apply again this argument, maybe you get another birational map and so on. This has to stop after finally many steps just for some simple topological reasons. You cannot collapse curves infinitely many times. It just has to be finite. And finally, you end up with precisely a minimal model or modified. So this is one possibility in the first step, but we have another for a different possibility now. L is not big. This exactly means that self-intersection is equal to 0. It also means that F is not birational. So, in other words, this guy is actually a vibration. Well, in this case, what I do is put that to be equal to, this is just a change of notation, it doesn't really do anything. Just put z to be equal to x prime so that you have now vibration. So we already have a more defined. So here your x is already fibered over some set, and the fibers are all negative because of, you see that if you take any curve inside a fiber, then intersection with L is equal to 0, but you have this ample divisor here, means that it must be negative on the fibers. So in other words, I have a more defined system. Now what is the conclusion of this couple of paragraphs is that if you have this assumption, where I did that. So if you have this kind of properties, if you can show that these kind of divisors are semi-ample that define morphisms for you, then it will give you this minimal model program for free, essentially. In higher dimension, this will be more complicated, but the idea is really pretty much the same. So it all boils down to be able to prove this kind of statement. You have some divisor of this form, and you should show that this is semi-ample. Now, if you remember, one of the remarks that I made in the first lecture was about precisely something like this. I told you if you have L of this form, you want to show that it is semi-ample, you could try to do induction using like Kodaira vanishing. But the problem is we don't have Kodaira vanishing, this is positive characteristic, so we should prove this in a different way. And now I tell you how to do that. So let's go to the, maybe in a sense, the important case. Assume that L is P. So let's consider one important case. Assume that L is P. So bigness here, as I said, also has a numerical meaning. The self-intersection is positive. Now, in this case here, I need to use a very important theorem of Keel, which is actually central to this whole story of all these lectures. So it's a good place to remind you of this theorem. This is the freeness theorem of Keel. Oh, actually, you could say it's semi-ample. I will discuss this in detail. Actually, I will give you the proof in lecture 3, the next lecture. But for the moment, let's just see what is the statement. So here, I have x. This x is very general. We don't have to the x. The surface x is a projective scheme. So it does not even have to be irreducible. It could have non-reduced character. It's quite general. Suppose that x is a projective scheme over K, and suppose that L is some Q-Cartier device. So it means that it could have rational coefficients, but you can actually just assume Cartier. It doesn't make much of a difference. Suppose that you have, let's say, some Cartier divisor on some projective scheme defined over this field of particle characteristics. Now, define the following set first. Define the exceptional set of divisors to be the union of all integral subschemes such that L restricted to Z is not B. So here B is integral subscheme. Oh, sorry, I also forgot even net. This is very important. Otherwise, you cannot formulate it in this way. So L is a Q-Cartier or just Cartier divisor. It is NEF. NEF again means this positivity, intersection with every curve, non-negative. So I look at all integral subschemes such that restriction of L to V is not a big divisor, not a big Q-Cartier divisor. Then the statement of the theorem is that this L is semi-ample if and only if L restricted to this exceptional set is semi-ample. So in other words, to check that L is semi-ample or some multiple is generated by global sections is enough to only look at this special set inside.
This set is really like countable union, right?
It's actually a closed sum. It's maybe not so clear, but in the next lecture we will see that it's a closed sum. And the funny thing is that this kind of theorem failed in characteristic zero. There is no such thing over complex numbers. This is really a very characteristic P kind of statement. And the reason you can prove such a statement is precisely because of what I discussed in the last lecture. When you have a scheme and then you have a closed subscheme, and when you consider a thickening of this closed subscheme, you can understand freeness on the thickening by using Frobenius. So in characteristic P you can do this, but not in characteristic zero. That's why you can prove this kind of statement. Anyway, for the moment I just use this statement, I will prove it in the next lecture. So now you can think of the scheme X to be the X in the theorem, the L to be exactly the same. With the same notation, then I apply Keel's semi-ampleness theorem. Okay, let's see how we can apply. So as I said, we already have X, we have L. We need to see what is this exceptional set, the EL. But we are working on a surface, and the L is already assumed to be big. So we go back to the proof. So L is X is the surface, the dimension 2, and L is, by assumption, a big divisor. So in particular, this means that X itself is not inside this exceptional set. It should be something strictly smaller. But a closed set inside a surface will be just a collection of curves and points. But actually, if you look at the definition, it's ruled out points. There should be only considering curves. So, of course, this depends on convention, but let's assume, make it clear the dimension of the positive. So, if you have a divisor on a point, you could say by convention that this is already big. So, you can exclude all points. So in other words, here we have just a finite set of curves. And Keel's theorem says that it's enough to show that L restricted to this collection of curves is semi-ample. So the good thing about this whole thing is that you start with a surface, now you work on curves. You drop the dimension by 1. So you can talk about induction. But to do induction, you have to do it in a way such that what you get in lower dimension should be similar to what you started with. And I tell you how to do this thing. So we can actually change the whole setting for not so difficult reasons. But I will not go into these details such that we could assume, or if you are not happy with this thing, you can just assume we are in this special situation. You could assume that the connected components of EL are all irreducible. I mean, the thing is that if you have different components, there are some tricks to get rid of them one by one and end up with just one component. So we have a disjoint union of just irreducible curves. So irreducible curves is kind of easier to understand than having several components. Now pick a component of of this exceptional set, EL. So I only need to show that L restricted to such C are semi-ample. Okay, how we do this? Well, now the L is big, therefore, actually for not so difficult reasons, again, more or less simple reasons, we can write the L in a linear sense, but out to rational numbers. So here it means that ML is linear to MG. So you see that in many situations we need to consider rational coefficients, so the definitions are all asymptotic. They are defined out to some. Anyway, you can just assume L is linearly equivalent to some effective divisor such that this C is a component of this divisor C. Actually, the next lecture we will see we have a more precise, actually much more precise formulation of this kind of relation. Anyway, so I can make sure that C is inside one of these effective divisors, and now let alpha be the number such that the coefficient of this C in the divisor T plus TA is come from L, and then I also need to add alpha times T. So I want the coefficient of C in here to be just exactly 1. So the ample guy here, A, because it's ample, you can actually just change it and make sure that it does not cause any trouble. For much of this kind of algorithm, you can just ignore it. So it means that you just need to see what is the coefficient of C in P, and then if it's not equal to 1, you add enough multiples to make it equal to 1. It's just a very artificial
kx.
argument.
Do you have to add kx to this expression?
No, I want to choose a k out. Because I will try to apply adjoint. Okay, so we have this then. Let's call this delta. So C is a component of delta with coefficient equal to 1. Now, if you look at your notes and look at the beginning where I talk about adjunction, this is precisely that kind of situation. So I can apply this adjunction formula. So by adjunction, there is some effective divisor. Let's call it delta. Here on the normalization such that the pullback of this k plus delta to the normalization of this curve is exactly k plus this divided delta c. Okay, I apply this adjunction, I have the normalization and I have some effective divisor. But since C was inside of L, just pretty much from the definition you can see that this actually exactly means that C intersection with L is 0. This is because we are on a surface, we are looking at those curves on which L is not big, but not big just means intersection equal to 0. And because the T divided T is essentially the same as L, so it does not change intersection numbers, it also implies that Kx plus delta intersection with C is equal to 0. And when you go to the normalization, this just means that degree of K C nu plus delta nu deduction is not equal to 0. So remember that these guys are effective divisor. You have some curve, canonical divisor plus effective. In fact, it is not only effective, but it cannot be 0 because this ample divisor here. So the pullback of ample is always ample, it cannot be 0. So this is not 0. It contains some ample divisor. Well, this implies that the degree of the canonical divisor should be negative. And there is only one possibility. The possibility that this curve should be exactly the projected line. Because if it is elliptic, degree will be 0 plus something, which already has positive degree cannot be 0. So if somehow forces this curve to be of something very special type. But you can actually say more. This curve, so you have the C itself maybe something like this, and then you have C nu, this is the normalization. If you have a singular point, for example, of this form, on the pullback here on the normalization you get, for this example, you'll get 2 points. And the thing is that the canonical bundle of such a curve C is already not negative. It could be 0 or it could be positive. So when you go to this C nu, you will have here, for instance, you will have 2 points. That's already degree 2. And we don't even take into account this ample divisor. So what I'm trying to say is that if the arithmetic genus here is not equal to 0, the degree here should be more than 2. And this is a contradiction, which is not fun. Therefore, in fact, C already should be smooth. So in other words, you have just a rational, smooth projective line, which is exactly this component of EL. But if you have any divisor on the projective line of non-negative degree, it's semi-ample for really stupid reason. So this in particular implies that L restricted C is in fact semi-ample. Sorry. That's just because of the way projective line behaves. So we have verified that L restricted to every component of this exceptional set is semi-ample, and therefore L itself is semi-ample. And this is exactly what we were looking for.
That's because you assume L is net, right?
Yeah, of course, this intersection number, anyways, is 0, so this is numerically equivalent to 0. On P1 numerical, that means linear.
So at the beginning of the proof, there is a, well, we're assuming if so there is a C where L intersect with a C has is less than 0.
That was K plus B. Intersection C equal to, it was negative and then
Right. So
we added some.
is there any relation between this C and the C here?
Actually, they are not precisely the same, but some of them will be. Actually, they will be essentially. They will be among, not all of them. So if L intersection C is 0, then it implies this is negative, just because of this ample divisor you have. But this may not hold for all the curves satisfying this thing. The point is that you could choose your ample divisor, maybe you have to change it around so that you can capture one of these curves. Yeah, okay, so that's the case of B, and then you have other cases. That's actually not the end of the story. You have the case when the divisor L is not B. But if the divisor is not big, you have, again, several cases. If quadratic dimension of L is equal to 1, so L big means quadratic dimension 2. Now you can go to the next step, quadratic dimension 1. Then actually here, the argument would be, in a sense, easier, then there will be already a fibration. I mean, it's actually quite easy. For some easy argument, there will be a fibration, let's say x to z, such that if L is a pullback of some divide, maybe up to some linear equivalence. And then in particular it means that in fact it is already a more refined. So this is in a way is easier. But you have other cases. If quadratic dimension of L is equal to 0, actually in a way this is much more difficult. Yeah, you have to use quite different methods. Show that L is actually semi-ample. And finally, you also need to show that quadratic dimension cannot be negative. again, this goes through quite different methods. I don't discuss these things because you see, in the big case, it somehow also works in higher dimensions, or expected very much to work. It's already on threefold, actually, more or less it works. But these methods, already on surfaces, they are quite complicated. And for threefold, there is no reason to see why they should work. So at least no one really knows. So that's why I don't go into this detail. I think the big case was maybe the most beautiful in this story. Yeah. Okay. So this is the minimal model program, and then you have the so-called classification.
So for this, you mentioned quite different methods. Do you still need to go back to the old method, to Mumford?
Yeah, exactly. Mumford method. So it's actually also quite similar. There is some similarity with complex case, but the characteristic feature is more different. You cannot certain methods that are available in characteristic field. But it has a kind of very combinatorial nature. For the moment, actually, I have used similar things for threefold.
I guess that's the point. When Mumford did a classification, service classification category P, and he sort of developed something to replace the quadrilateral vanishing, but using some.
Yeah, but the thing is that because you are a surface, you can do a lot of combinatory.
Yes.
It's easier, but when you move to the next step, which is threefold, then this thing breaks down. It becomes much more complicated. So the bottom line is that you have to find better ways to deal with these cases that I did not discuss. Anyway, classification here, I cannot really say much because if you are interested in the standard place to look at it, is Mumford. So they consider this classical case when there is no divisor B. Just you start with smooth x, you find the minimum model and try to classify. Anyway, I'll just say, just if you think about this case. So suppose that we have xp projecting on dimension 2. Now, so in the last year I told you essentially how to find a minimal model for a more defined space. So these kind of surfaces are divided into 4 different categories. So assume y, by is the minimum model for more defined space. So we have several cases. When the quadrilateral dimension of divisor kf plus p is minus infinity, which, by the way, is always coinciding with the quadrilateral dimension of y b1. So when this is minus infinity, that means that you are definitely going to find a modifier, not a minimal model. Because exactly this negativity here gives you negativity in terms of geometry. So then, this means that there is a modified structure on Y. You have a map to some set, this is a vibration, and ky plus by is negative. Defined. So we could say more things here. For instance, if you care about just classical setting, not singularities and no divisors, if x is smooth, b is equal to just 0, then in fact there are a few possibilities here. So in this case, you either have a point which means that the y should be or Z could be a curve, which means that Y is the rule surface. So in other words, there's a P1 bundle over the base. These are the two possibilities. So either you just end up with essentially with P2, the projective plane, or you will end up with the P1 bundle over some curve. So these are already classified. That's one case, and another case is when K plus B is the quadratic dimension equal to 0. So as I said, it's again just equal to the same quadratic dimension on Y. And here, what you can say is that Ky plus Py is torsion. Or you could also write it in this form, just a torsion bundle. So for instance, if X is smooth, B is 0. So for instance, you could get so some of the most important cases would be, for instance, Y can be an abelian variety. It could be a K3 surface, and so on. So again, there is a kind of classification here. So you know a lot of detailed things about this kind of surfaces because they are so special. The X itself could be complicated, but the Y is very simple. And then you when quadratic dimension is 1, then you have some elliptic vibration. So with fibers of arithmetic geometry 1, for instance, just elliptic curve, or singular rational curve. So the fibers are very special. You can understand this Y just by looking at the fibers and looking at the base. The base here will be some smooth curve. I've already found it there. So I will, okay, maybe just stop. Modulus here, quadratic dimension 2 is much more complicated. There is no simple way of classifying these things because there are just so many possibilities. But you could still say that there is some morphism from Y to maybe Y prime such that your divisor is the pullback of some ample device. So actually somehow there is a very important statement somehow hiding behind this statement is that in these three cases when Ky plus By has the positivity condition, here you have a torsion, here it says that it actually defines them up to some curve, here it says that defines them up to another surface. This is birational. But this is just saying that Ky plus By is semi-ample itself. And this is the statement of the abundance theorem. So in last three cases, Ky plus By is and this is probably in higher dimension of this is not known even in characteristic 0, nominally up to dimension 3. This is probably proving such a statement is the most important question in birational geometry in both characteristic 0 and positive. Again, if you want to get the field method, this is definitely the kind of thing to think about. I will stop.
Any questions? Okay, let me remind you again. So next week, the following 4 lectures, the time is at 3:30 and at 5 o'clock. If not, no more questions, let's thank you for your part.